So much then for the logical operations of our conditional operators. Now these are all the operators we're going to see in terms of truth functional connectives, not, or, and, if then, and if and only if. But there remain some very important and interesting questions about this whole system we've constructed so far. And there are basically two of these questions that we're going to address here. The first is whether or not our system is sound. What this means is that if there's a proof of something in our system, then that argument that we've proved is valid. The second is whether or not our system can prove every valid argument. To clarify, here's an example of a system that's sound but not complete. Suppose we took the fragment of our deductive system which just deals with conjunction, introduction, and elimination. So from P, Q, we derived P and Q, and from P and Q, we derived P, we derived Q. That itself is sound. We're not going to come up with an invalid argument in that system. But it's not complete. There are further arguments, like modus ponens, if P then Q and P, therefore Q, that themselves are valid, but can't be proved in our conjunctive fragment of the Fitch deductive system. So there's a system that's sound but not complete. In general, completeness proofs are quite difficult. Soundness proofs are usually quite easy, although they sometimes involve a little bit of drudgery. This final lecture just gives a sketch of what a soundness proof for our Fitch deductive system would look like, and sets aside the question of completeness for a later day. The point here is to speak more generally about deductive systems rather than just about arguments the way we've been doing up till now. So suppose we have a deductive system D. So D is sound just in case only valid arguments have a proof in D. That is to say, we can't prove anything invalid. On the other hand, D is complete if and only if all valid arguments have a proof in D. Now you might wonder what kind of validity here we're talking about. And the answer, at least for the present purpose, is tautological validity. That is to say, validity that depends on the rules we've introduced for our Boolean operators and for our conditionals. We leave equals out of this because it's a complicated example since it's really a predicate. Now we've already seen that there are analytical consequences that are not themselves provable in the system that we've developed. For instance, here's an argument that is valid but not tautologically valid. We could prove this if we used the notion of analytical consequence. A is a cube, therefore A is not a dodecahedron. But we can't do this on the basis of our logical symbols up here. So what we're really concerned with for our present system is tautological validity. Now soundness is relatively easy to show, and completeness is somewhat difficult to show and will involve conceptual apparatus that we'll develop later on. The main point of this video is to get clear on the distinction between these two concepts and to provide a brief soundness proof for our proof system Fitch, which we've been using so far. And what this amounts to is showing that if there's a proof in Fitch of some conclusion from a set of premises, then that argument from those premises to that conclusion is tautologically valid. So, to put this slightly more formally, we would say, if P1 through Pn entails, say on Fitch, we can use a subscript F to represent our system Fitch, a conclusion S, then S is a tautological consequence of P1 through Pn. So this is our notion of soundness, and this is what we're undertaking to prove for this video. Now, just one quick remark on this word soundness. It might seem a little bit confusing to refer to soundness in this way. What we might want instead is to say that we're trying to show the validness of our system Fitch here. But the convention is to use the word soundness, and it here doesn't really have much to do with the notion of soundness in the sense of an argument. We're talking about soundness of a system, and what that means is that it proves only tautologically valid arguments. If we recall our proof system, which is F, then we know that if P1 through Pn appear, then we're allowed to assume them in our deduction of S. And that is true even if S is buried deep within a sub proof. So for instance, all the way down here we still get S. S just depends on all the prior assumptions that are in force that are in what I've been calling superproofs in the main line here, or in our set of premises up above. And we want to show that if S follows from these, then S is a tautological consequence of these. And we'll do this by contradiction. And we'll do it by a contradiction on a proof by cases. The way to do this is to work through each of our rules for all of the Boolean operators as well as our conditional signs, and to show that they preserve tautological validity. If we assume that they don't, we come up with a contradiction. So let's just do one here. Let's look at the rules for the conditional arrow. That is, for the material conditional. So suppose that our rule for condition introduction is invalid, and this is to give an indirect proof or a proof by contradiction. So we'll say for reductio, or for an indirect proof, that is to say a reduction to the absurd or a contradictory conclusion, assume at least one application of the conditional introduction rule is not tautologically valid. So picture that we're just moving our way through a proof, and we assume P and we derive Q. Up to that point we're okay, but then we get an instance of if P then Q, which is false. Now take this part right up until we make our putatively invalid step, and let all of the assumptions in place be A1 through AK. These are just the assumptions that we're entitled to draw on in the course of our proof. So A1 through AK include premises, things we've proved already, so prior sentences in our proof, and subproofs that we're in, i.e. assumptions we haven't discharged by closing the subproof. So at this point, we'd say A1 through AK on the assumption of P make Q hold, but they do not make if P then Q hold. But wait a minute, if they make Q hold, then they lead from whatever value X to T. So just to make this clearer, recall our truth table here for the material conditional, and notice that the only place in which it comes out untrue is when we go from a true sentence to a false one. But wait a minute, if we look back over here, we see that A1 through AK already support the deduction of Q, which is to say, assuming that they're true, then it's true as well. So how can we go from T to F if we already have a T? So our assumption that this instance, some instance of the conditional introduction rule is invalid leads us to a contradiction, because it compels us to say that we have a true sentence, Q, on the basis of these prior assumptions, which nevertheless does not follow from this assumption P, which should suggest that Q is false, but actually it's true. And there you go. So we can say that, at least with respect to the conditional introduction rule, our system F is sound. Now we've already seen that we have several operators and rules for introducing and eliminating them. And so the way to construct a proof that the whole system, which just consists of those rules, is itself sound is to show that each of those is valid, and so it amounts to a great big proof by cases. So here's how the roadmap for constructing a full soundness proof would look. Take a rule that we use in the course of our deduction, call it rule flower. Well, rule flower equals one of the following: negation elimination, negation introduction, disjunction elimination, disjunction introduction, and so on. In all then, a pair of rules for each of the signs that we have. And then we take each of these and we construct a proof by cases, showing that if it's negation elimination, it's valid, showing that if it's negation introduction, it's valid, and so on, until we've exhausted all our rules. And that's what a soundness proof looks like. And in this case, we used indirect proof by assuming the opposite of what we wanted to, and that's what got us where we wanted to go. It would just be a question of constructing a string of these proofs, and again, the whole thing would amount to a great big proof by cases. Rule flower is one of these rules, and once we've exhausted them, we've exhausted all our cases. Now we can wrap this up in just a minute, but I want to end with two observations. The first is about our overall proof by cases here. So if all of these are valid, then Fitch is sound. And now we can see why we might want something in the way of simplicity when we're proving things about our systems. Now we saw earlier that we have this symbol here, the Sheffer stroke, which is equal to neither nor, so that P Sheffer stroke Q is equivalent with neither P nor Q. And we saw that this whole thing is truth functionally complete, which is to say, if we wanted to, we could express all of the Boolean operators as well as the conditional operators merely in terms of the Sheffer stroke, merely in terms of neither nor. And you might think, well, if you're trying to use a deductive system, why would you want to do that? But notice that if we had rules for the introduction and elimination of neither nor, our system might be a good deal simpler, and therefore this proof of cases over here would be a lot more straightforward. And this is why logic tends to err on the side of parsimony in terms of logical operators, unlike things like the computer sciences, which have fancy operators like nor and zor and so forth. Having these is great for conducting operations, but if you're trying to prove something about your system, then adding these in here is going to make your proof by cases a good deal more complicated. We want to keep things relatively simple. But again, it's a bit of a balancing act between simplicity in terms of proving things about the system and relative flexibility in terms of use. I think that if we were teaching this course using just the Sheffer stroke, people would not be having as good a time. That's the first observation. The second observation is that, in a way, the soundness definition tells us that if an argument is invalid, then it doesn't have a proof in our deductive system. Completeness, on the other hand, tells us that if an argument is valid, then it does have a proof in that system. We sort of glossed over this issue here of what kind of validity we were talking about by just straightforwardly going with tautological validity. But as we've seen, of course, there are plenty of arguments. Again, something like if we say A is larger than B, then it follows that B is not larger than A. But this is not something that we can prove in our deductive system Fitch. Now, if you'll recall from earlier, though, larger, of course, is a predicate, and so is equals. And we've actually incorporated equals into our system as something like a logical constant, although we haven't been discussing it in the course of this lecture on soundness and completeness. So in a way, we've kind of tipped our hand. We could make predicates into things we have introduction and elimination rules for. And in that sense, we could introduce a great deal more arguments that are analytical consequences, but not tautological consequences. The problem is that doing so would introduce a lot of rules very quickly. For instance, to make this A is larger than B, therefore B is not larger than A, into a valid argument in Fitch, we would have to come up with rules governing the use of the predicate larger, the way we did with equals. And in general, you might think that there's a bit of give and take between soundness and completeness, especially since we've been showing here that showing that our system is sound is a matter of showing that it can provide proofs only of valid arguments defined in terms of tautological validity. But on the other hand, there might be other arguments that we want that go beyond tautological validity, that go into something like logical validity or even Tarski validity, where say, if something is not a cube or a dodecahedron, then it's a tetrahedron. This is a very difficult question. I only mention it now to say, if you think there's something a bit limiting about our restricting our notions of soundness and completeness for deductive systems to merely tautological validity, as we've done here, you're not wrong. But given that validity is a term that is ambiguous between logical validity, tautological validity, and even more broad and out there kinds of validity, we need to kind of pick and choose how we're going to do this. And tautological validity at least provides a nice and straightforward way of doing this. But again, there might be other things that we want to prove that aren't provable in our system, even though we regard it to be sound and complete. So there is a very important and ultimately a philosophical question about what a deductive system should enable you to prove. And if you think that's interesting, I would encourage you to continue thinking about that. And that's it for week 10. So, as ever, just let me know if you have any questions, and I'll wait to hear from you.